will proceed in innovative approach in calculus, and we will see multivariable, Taylor and Maclaurin polynomial approximation. Polynomial approximation, one of the most pioneer thing that came in calculus. Polynomial approximation. If I have an algebraic equation, then can I rewrite that algebraic equation in terms of polynomial? This is a something that is very big and new thing that came into the picture. Initially, this draft was proposed by Mr. Talon, and later, as a special case, it came from Mr. Maclaurin. Polynomial approximation of any algebra. So if I have algebra that is sin x, then can I rewrite as a constant plus x to the power 1, constant plus constant x to the power 1 plus constant x to the power 2 plus constant x to the power 3 plus constant x to the power 4, and so on, and then constant x to the power n. Anyway, any algebra, either it is e to the power x, tan x, sin x, log x, whatever comes to anyone mind. If I have bunch of algebra, if I have if I have bunch of algebra, the algebra I have bunch in the sense that I have a mixture of algebraic equation where sinusoidal is there, tangent is there, exponential is there, logarithmic is there, polynomial is there, then multiplication is there, addition is there, subtraction is there, and division is there. Everything is in kind of in a bunch, in a block box. If it is in black box, then can I represent it as a series of polynomial equation? This is also called polynomial polynomial x polynomial approximation. What is your fx? Someone is asking, what is your fx? Fx, function over x. What is your fx? Fx is very big thing. What is your big thing? Big thing is it is sin x plus tan x plus e to the power x by log x plus sine square plus cos, so many things. This big it is. If I ask, can you calculate integral calculus? Impossible. No way. How it's possible if someone rewrite this algebraic equation as a series of polynomial equations, polynomial approximation, then it is quite easy. But at the end, it is approximation. As I say, there are many times where integration is absolutely not possible. By any means, it is not possible. Then generally people go for numerical approximation, where you have a graph that divide graph into n different parts, and in a particular part take any height or middle height or first end and middle average height, and then multiply by the width. That region you get the area. Calculate all the area, add all the area, you get the integration. That is the integration. At the end, integration is area. What about 3D integration? Area. What about 4D integration? Area. Okay. Integration is nothing but calculating the area, but I am calculating the volume. If this is xy plane and this is the surface, if I integrate this surface with the xy plane, it gives the underneath volume. Okay, it is calculating underneath area only. The way dimensionability has been placed there, it looks like a volume. Anyway, so integration is nothing but a way to calculate the area. But many places we are not able to calculate the area. In that terms, we go for numerical mathematics and calculate the net area. Or we can go by the polynomial approximation. But polynomial approximation is very big thing. Anyway, now there are two things. One is Taylor series, one is Maclaurin series. What we talk, Maclaurin series is considered as one special case of Taylor series. What we talked about in previous video, if I have any function fx, if I have any function fx, and fx is nothing but a well behaved polynomial equation. Fx is nothing but a well-behaved polynomial equation. So if that is the case, then if I go with the how we calculated the polynomial approximation of a polynomial. If I have a polynomial equation, can I replicate this polynomial equation into another polynomial equation where from this I need only derivative as the information? That is the crucial point which triggers to calculate the polynomial approximation of any algebraic equation. So we tried with the simple polynomial equation fx equal to a0 into x to the power 0 plus a1 x to the power 1 plus a2 x to the power 2 plus a3 x to the power 3 plus an x to the power n. If I calculate fx when x equal to 0, then fx is equal to a0. So a0 equal to fx when x equal to 0. Now, if I differentiate it dfx by dx and calculate the value when x equal to 0, then it becomes equal to a1. Others are 0. If I calculate d2fx by dx square and calculate it when x equal to 0, then first two terms gone, and then it is 2a2 plus in x. So a2 is nothing but d2fx by dx square by 2. If I go for triple differentiation d3fx by dx cube, then first three terms gone. Now it is 3 into 2 into 1 a3. That's it. So a3 is nothing but d3fx by dx cube into 1 by factorial of 3. Okay, this way we are getting the constant against the each x to the power in the equation. Now if I rewrite fx with the differentiation, then fx equal to a0 then dfx by dx a to the dfx by dx into x plus 1 by factorial of 2 d2 fx by dx square into x square plus 1 by factorial of 3 d3 fx by dx cube into x to the power 3, because all those constant we are replacing with the, this is what is the replica. This is called replica. If I have any polynomial equation, I can create exact replica of this polynomial equation as another equation. Okay, if this is fx, then I can have another function written gx, which is exact replica of fx. What gx need? Gx construct a mathematical equation in that it needs information from fx only in terms of order of derivative, with no order of derivative, first order derivative, second order derivative, third order derivative, nth order derivative, and then it forms the equation as a0 plus dy by dx x plus d1 by factorial of 2 dy by dx d2y by dx square x square plus 1 by factorial of 3 d3y by dx cube x to the power 3 and so on. Okay, so that is called polynomial approximation. But this is indeed actually it is Taylor series, but it is a kind of a special case. What is a special case? We are considering x equal to 0. That is the special case we are taking when x equal to 0. What about x equal to any value called alpha, or x equal to any value called x0, x and at the bottom 0, x0. Okay, so if I have any value along the x-axis, this is x-axis, this is y-axis, this is, okay, so this is x-axis, this is y-axis, this is origin. This is x-axis and this is y-axis. This is the origin. What about now? There is a graph like this. There is a graph like this. If this is the graph like this, we calculated dy by dx only at the origin, and that's how we came up with the polynomial approximation of any function fx as a0 plus dy by dx x plus d2y by dx square x square into 1 by factorial of 2 plus d3y by dx cube x to the power 3 into 1 by factorial of 3 plus a plus dny by dx to the power n x to the power n into 1 by factorial of n. This is polynomial approximation, but when x equal to 0. What about x equal to x0? What about I want polynomial approximation when it is x0? I'm not talking about this. Okay. So there are few points here. This is origin. This is origin. This is x0. This is some point. This is x0. If this is x0, then this height is y0. This point is x0, y0. This point is x0, y0. Now, if I calculate differentiation of this curve at x0, y0, then dy by dx at x equal to x0. Now, we have polynomial approximation. That is fx, means y equal to a0 plus dy by dx x, leave the other terms. a0 dy by dx x. Now a0 I can keep this side. Now it is y minus a0 equal to dy by dx into x. This is a form when we calculated dy by dx at origin. dy by dx at origin, if we calculated a0 talks about the interception on the y-axis, where the interception happens on y-axis. Now we want dy by dx at x equal to 0, not at 0, at x0, x and 0. There is some point called x0. So in our equation, this is origin, this is x0 point, this is some point. x0 corresponding to x0 is touching the curve here. This point is x0 comma y0. This is the point x0 comma y0. If that is the point x0 y0, this point is, then what about the curve equation? What about the first order polynomial approximation? The first order polynomial approximation is fx equal to a0. a0 is interception on the y-axis. Okay, this is a0 where it is intercepting the y-axis, plus dy by dx into x, where dy by dx is calculated at the origin. What about if this is x0, then here this is x0 y0 point. What about if I calculate dy by dx here? What about this polynomial approximation? y minus a0 equal to dy by dx calculated at x0. dy by dx is nothing but slope at x0. If this point is x0, y0, then dy by dx talks about the slope. So, if I say y minus a0 equal to dy by dx at x0 into x, it talks about a straight line. If you see clearly, it talks about a straight line. If I just remove a0, then y equal to dy by dx into x. dy by dx is a slope, dy by dx into x. This talks about a straight line. Y equal to dy by dx into x talks about a straight line that has slope as dy by dx at x equal to 0. dy by dx at x equal to 0. dy by dx may come in algebra. dy by dx may come in an algebra. If that is the case, then dy by dx, whatever algebra comes, substitute x with x0. It will come a numerical value. Y equal to a numerical value into x. Y minus a0, that is the actual term 1. Y or fx equal to a0 plus dy by dx x, where dy by dx at x equal to 0. Okay, y minus a0 equal to dy by dx into x. Okay, this talks about if I remove a0, then y equal to dy by dx into x, where x at x equal to x0, whatever it is. This line must pass through the origin. That is the line. If I place y minus a0, then there will be shift in the line along the x-axis, whatever it whatever it is. At x0, if I talk about x0, okay, if I talk about x, this is origin, this is x0, this is the point. This point is x0, y0. If I have dy by dx at x0, y0, then if I draw a line y equal to dy by dx at x equal to x0 into x, it talks about a line that is tangent at this line. This is polynomial approximation. Single order polynomial approximation. Single polynomial approximation always happens, generally happens, or always happens at a particular point. We talked about polynomial approximation at point x equal to 0. Now we can have polynomial approximation at x equal to x0. Okay, so at any x equal to x0, if I go with the first order polynomial approximation, then any x equal to x0, it talks about the tangential line. This is also called local linearization. Local linearization means if I take any point on the curve, then what is the tangent point or linear? If I have a curve and if I see from near, like I'm sitting on earth and it looks flat, though earth is not flat. If someone sees, or someone is seeing moon as a round shape, anyone would say it's like a ball, football. But if someone really go to moon and keep going towards moon, at one moment he will start seeing flat. Moon is not round. If he goes near the moon, there will be one point will come that he will see flat. At that point, so moon at any point it looks flat. That is called local. This is called typically local linearization. So if someone is seeing the curve from very near distance, at one point it will look like a flat line. That flat line is tangential line. Tangential line is nothing but polynomial approximation of degree 1. First order degree polynomial approximation is nothing but local linearization, special case, whatever it is. Now we are talking about Maclaurin series and Taylor series. Now the actual Taylor series is, can we came to equation. If you watch previous video, we for any algebraic equation, we try to get the zero order derivative, first order derivative. Polynomial equation can be written as fx equal to a0 x to the power 0 plus a1 x to the power 1 plus a2 x to the power 2 plus an x to the power n. This is a typical way of writing a polynomial equation. If I try to copy it, duplicate it, then I can duplicate it just knowing the zero order derivative, first order derivative, second order derivative, nth order derivative. If I know those derivatives, then I can rewrite polynomial equation at fx equal to a0 when x equal to 0 plus dy by dx into x, dy by dx calculated at x equal to 0 plus d2y by dx square calculated at x0 into x square plus dny by dx to the power n, x to the power n, I'm sorry, I'll rephrase it, fx equal to a0 calculated when x equal to 0 plus dy by dx when x equal to 0 into x plus 1 by factorial of 2, factorial I was missing, 1 by factorial of 2 d2y by dx square calculated when x equal to 0 into x square plus 1 by factorial of 3 d3y by dx to the power 3 x to the power 3 where d3y by dx to the power 3 calculated when at x equal to 0. Like that, at the end, 1 by factorial of n d3 dny by dx to the power n into x to the power n. This is the polynomial approximation of a of another polynomial expression, that is a0 plus a0 plus a1 x plus a2 x square plus a3 x to the power 3 plus an x to the power n. But since these two are dependent only through the derivatives, now the first a1, a2, a3, what the polynomial equation we are saying, that I can replace with any algebraic equation. So any algebraic equation, if I have zero order derivative to n order derivative calculated at x equal to 0, I can rewrite in a form of polynomial equation. This is the scenario, and this is how Maclaurin he wrote the polynomial equation for sin x, tan x, cos x, e to the power x, ln x, log x, everything he wrote. He calculated the derivative at x equal to 0 and found out. But what about derivative calculated at any point x equal to x0? That is the scenario. That is the Taylor series. When x equal to x0, when x0 is 0, then it becomes Maclaurin series. Maclaurin series is a special case of Taylor series where x0 equal to 0. But if I try to calculate derivative at any point x, why derivative at any point x0 is required? Because sometimes we need to calculate the polynomial approximation at any point x0. If this is x-axis, this is y-axis. This is x0. This is some point. If this is centered at the origin, then this is the radius. This is origin. This is any point x0. This is any point x0, y0. If I have polynomial approximation, first order only, then that equation talks about tangent line at that point. It has importance. Just to calculate the tangent at any point or linear localization, just calculate the dy by dx where x equal to x0, then y equal to dy by dx into x talks about the tangential or local linearization at that point. It has importance. It has many importance that we will talk. What about the actual equation that Mr. Taylor brought in? We also brought in, but it was invented earlier because we need it. Many places we need it. That's why we invented it. In that scenario, now let's see the polynomial equation for which we calculated the replica. So actual polynomial equation is fx or y equal to a0 plus a1 x plus a2 x square plus a3 x to the power 3 plus an x to the power n. Now consider this is the polynomial equation. This equation passes through a point called x0, y0. If you remember, we talked about a straight line. That is the simplest case. If this is x-axis, if this is x-axis and this is y-axis, if this is x-axis, this is y-axis. In that sense, there is a line like this. What is the equation of this line? Where slope is m, then y equal to mx. That is true, but it talks about the line that passes through origin, not this line. If that is the case, then it will be, I have to find interception at y-axis, where it intercepts. If it intercepts y at y0, then it is y minus y0 equal to mx. No. I know where it intercepts on x-axis. It intercepts at x0. If that is the case, then it is y equal to m x minus x0. Okay? No. It passes, this is the line for which I have to find the equation. Then this line, if I talk this point, this is x0, y0. If this is the line, there is a point called x0. If I go up and touches the line, then at this point, the point is x0, y0. That is x0, y0. Consider this. Then what is the equation of the line? I'm not talking about interception at y-axis, interception at x-axis. I'm talking about any point on the line. Any point on the line is x0, y0. If that is the case, then what is the equation of this line? Provided the slope of this dy by dx, slope of this is m, then it is y minus y0 equal to m x minus x0. If interception at y-axis is y0, then it is y minus y0 equal to mx. If interception is on x-axis, then it is y equal to mx minus x0 in braces, m outside and then braces x minus x0. If it passes through a point x0 comma y0, then y minus y0 equal to mx minus x0. Okay, where we can now, what about m, slope? Slope is what we calculated at x equal to x0. This is the representation. If I have a slope of a line that is calculated at x equal to x0, then y minus y0 equal to dy by dx at x equal to x0, x minus x0 is the equation of the line. Similarly, if I have a curve fx equal to a0 plus a1 x plus a2 x square plus a3 x to the power 3 plus a n x to the power n, and it passes through a point called x0 y0, x0 y0. If that is the case, then this equation can be rephrased as fx function over x equal to a0. A0 is nothing but y0 here. Fx equal to a0 plus a1 x minus x0 plus a2 x minus x0 whole square plus a3 x minus x0 to the power 3, like that an x to the x minus x0 to the power n. If that is the case, and someone would try finding dy by dx when x equal to x0, then other term will keep becoming 0 0, the way we did in the, we'll try. What about fx when x equal to x0? All will become 0 and fx equal to a0. That is y0 I am talking about. Okay, if that is the case, then fx equal to a0. Now dfx by dx equal to what? A0 gone. A1 x minus x0. Then if that is the case, then it becomes A0. A1 equal to dfx by dx when I'm sorry, dfx by dx when x equal to 0. A0 term gone in first differentiation only. Second become A1. Third become A2. 2 into A2 x minus x0, x minus x0, like that x minus x0. Now if I set x equal to x0, all becomes 0. Now a1, the a1 becomes dfx by dx. So a1 I can silently replace as dfx by dx when x equal to x0. What is d2fx by dx square when x equal to 0? First a0 gone, a1 gone, a2 becomes 2 into 1 into a2. That's it. And plus the third term becomes 3 into 2 into a3 x minus x0 plus so on. If I set x equal to x0, all becomes 0. Okay, then x2 becomes 1 by 2 d2 fxy by dx square when x equal to x0. Same thing. Now keep doing that and it becomes a Taylor series. So what is Taylor series? Now I will do same thing I talked about. Okay, I do same thing I talked about. One person is carrying a algebraic equation. What do you have in your hand? In my hand, this is an algebraic equation. No. This is a tennis ball. This is not algebraic equation. This is a tennis ball. No, indeed it is an algebraic equation. It is a mixture of algebraic equation. Algebraic equation is a mixture, and mixture is kept inside this ball. What is your mixture algebraic equation? That is sin x into tan x plus x square by cos square plus exponent e to the power x into cosine x, like that. It's a full bunch of mixture of algebraic. This is fx. So I have kept inside a ball. I call it as a black box. This is my algebraic equation. Can you reproduce this algebraic equation in terms of a, a polynomial approximation, in terms of a polynomial equation. Okay, what you want else? Okay, one thing I know that this graph passes through a point called x0, y0. Or this guy is saying, who is trying to reproduce this black box into series of polynomial equation, he is asking now, what is your zero order derivative at any point x? Do you know that it passes through a, what extra information you have? Okay, it does not pass through origin. This is what I know. Okay, it passes through what point? It passes through point x0, y0. If that is the case, what is the zero order derivative? What is the zero order derivative at point x0, y0? This is the zero order derivative. Now, this guy is following Mr. Taylor and he is saying fx equal to x0 plus a1 x to the power a1, 1 plus a2 x to the power 2 plus a3 x to the power 3. This is the Taylor series. Okay, a2, there I have to, this is the normal polynomial equation. A0 fx equal to A0 plus A1x plus A2 x to the x square plus A3 x to the power 3 plus an x to the power n. Taylor series A0 will be replaced by zero order derivative, means fx value when x equal to x0. A1 will be replaced by dfx by dx calculated at x equal to x0. This is what we talked, right? Now a2 will be replaced by 1 by factorial of 2 d2fx by dx square calculated at x equal to x0. Now a3 will be replaced by 1 by factorial of 3 d3fx by dx cube x to the power 3 dx cube. I'm sorry. And at the end, an will be replaced as 1 by factorial of n dnfx by dx to the power n. Okay, that is one case. Another case, wherever we see x, a0, a1x plus a2x square plus a3x cube, since it is passing through point x0, then x will be replaced by x minus x0 everywhere. So the Taylor approximation for any function would be first order derivative, zero order derivative means value of fx. If a person is holding a black box and he has an algebraic equation, the guy who is replicating, he is asking what is your fx when x equal to 0. Now he calculated, he settled all sin x, tan x, ex, log x at x equal to x0. Whatever value comes in, he is transferring now. Now he set it to a0, fx equal to a0. A0 is the value at f of the fx at x equal to x0. Next is dfx by dx into x minus x0, where dfx by dx calculated when x equal to x0. Now he is saying, can you give me the first order derivative? Okay, now he told, okay, first order derivative I have calculated at what point? X equal to x0. Whatever it came, now he replaced a1 with dfx by dx, first order derivative calculated at x equal to x0 into x minus x0. Give me second order derivative. Whatever he returns, then it becomes, now he replacing a2 with the 1 by factorial of 2 d2 fx by dx square calculated at x equal to x0 into x minus x0 plus, tell me the third order derivative. A3 x to the power 3 is replaced by 1 by factorial of 3 d3 fx by dx cube d3 fx by dx cube into x minus x0 to the power 3. What is your fourth order derivative? Now a4 is replaced by 1 by factorial of 4 d4 fx by dx to the power 4 calculated at x equal to x0 into x minus x0 to the power 4 plus at the end 1 by factorial of n dn fx by dx to the power n calculated at x equal to x0 into x minus x0 to the power n. This is the Taylor series expansion when calculated at x equal to x0. When it is calculated at x equal to x0, x0 still it is a variable that can be set at any point. But if it is set at 0, then x minus x0 all become x and dy by dx or dfx by dx has to be calculated at x equal to x0. It becomes Maclaurin series. Maclaurin was knowing about the Taylor expansion, but he calculated at x0 equal to 0, and he found very interesting sinusoidal, tangent, and so many trigonometrical equations, exponential, logarithmic, so many algebraic equations equivalent in polynomial equation. Amazing, right? This is Mr. Maclaurin did. Anyway, actually, I had thought that I would start the multivariable. We have talked only about the single variable x. X. What about x and y? What about x, y, z? What about x, y, z alpha? What about x, y, z alpha, beta, gamma? What about 100 component, 100 variable equation fx, y, z alpha, beta, gamma, and so that? We talked only about fx. If equation is fx comma y, if equation is x comma y comma z, whatever the solution that is available in book or internet everywhere, someone has to remember it mug up for fxy. For third, fourth, fifth person has to hit head in the wall. Not possible. Very difficult. Solution itself is based upon many assumptions, many kind of approximation. Okay, tends to zero, some kind of infinitesimally small region. If I take, then it tends to zero, and this kind of stuff. Not possible. Okay, what is our invention in that as far as multivariable is concerned? So that we will talk. Please support us. So this we are talking about innovative approach in calculus. Whatever invention we have done as far as calculus is concerned, and we have not done any invention. Actually, I thought in a simplistic way, because whatever I was reading here and there, it become impossible to understand. If you understand also or mug up also, next day you would forget. As long as you don't understand the concept behind it. The what is power of invention? How I can invent anything? You can invent anything only when you simplify anything. If you de-simplify anything, go into complex area and introduce variable by variable to solve it, it will become complex day by day. This is what we did anti of it. If I have x-axis, it is very fine. If I have x and y-axis, then I rather than considering x and y-axis, I started thinking as single independent component as xy plane. XY plane. Now again I have a single component only, that is XY plane, rather than two independent component X and Y. If I have X, Y and Z, then single independent component, that is X, Y, Z cube, rather than X axis, Y axis and Z axis, three independent. This approach would bring simplistic way in multi machine learning, and that also we will see. Dimension reduction ability, that is the future of the machine learning. There also we will see this approach where we make things simple. Whatever the problem is, try to bring problem into lower dimensionality. If I talk about multivariate x and y, there is no x and y axis. There is only one thing, that is xy plane. XY plane, XYZ cube, only one thing. If I tackle this with one go, then later I can distribute it. But people try to tackle with x-axis, y-axis, z-axis, unnecessary, then bring like Lagrange variable, bring a lambda, and this and that, and then do so many sideways invention that is no one is interested in. So if someone thinks about making anything simple, less dimensionality, he invent anything. Okay, he can do anything. Okay, so please do support us. +91 is the India country code. 9483160610 is the telephone number. 9483160610. +91 is the India country code. Okay, so please do support us, it helps. We will see multivariable in Taylor series, Maclaurin series, mind-blowing series.